Hey there, folks. Professor G here. How you doing? Um, Moving on with our next lecture here in astronomy, and what we need to change our focus to now is how we currently view everything that's all around us. Um, we've talked in the past about when you look up at night and you see the stars up in the sky. There's this you don't even do it on purpose, but there's just this implication in your brain that there's a ceiling up there. Okay, the planetarium effect, as I've called it before. We made our constellations based on that, and maybe you did know for that, oh yeah, that star isn't anywhere near that star, so on and so forth. But a lot of folks, it's not that they don't understand it or didn't get it, they just never thought about it. But these stars are many, many millions, trillions of miles away from each other oftentimes. But in order to process that, even for an astronomer, we still sort of pretend that there is this sphere out there, this globe. We call it a dome. You think of only maybe one hemisphere of the Earth, but it surrounds both sides, and it helps us. Well, it helps us process the data. Here's a picture of kind of what we're talking about. And you're familiar with coordinates, okay, like we use on latitude and longitude on Earth, okay? And we do the same thing with space. So you have the celestial poles, okay? And that's the north on the sphere, the south on the sphere. The celestial equator, okay, mimics our equator. And what you've got here is, because remember the Earth is tilted 23.5 degrees off center, okay, off straight up and down. So is everything else, basically. All right. And what that gives us then is, looking here, is this term called the ecliptic. And you're going to hear this word over and over and over again. And this is the band, the pathway that the sun and other stars um, move around. Okay, you'll see. I don't want to talk too much about it right yet. It'll come up. Don't worry. So it's not everything is sort of tilted, so to speak. All right, a couple more terms. These are relative terms. We've got zenith and horizon. These are for you standing on Earth. All right. Well, wherever you are, you look straight up. That is the zenith on the celestial sphere. If you are 100 miles away from where you were yesterday, you're going to have a totally different zenith than you did yesterday. Okay. Like I said, these are relative. Horizon, you wouldn't think would be relative, but you do see, as you move, you see different parts of the horizon. Horizon is a word everybody knows already. We watch the sun rise, the sun set, perhaps. Many of us see many more sunsets than we see sunrises. But as you're driving your car, staring forward, especially on a long trip, you can't help but keep your eye on that horizon. Neat thing, and I suppose I knew this at some point in life. For an average person, I think an average person's a little shorter than 6 foot tall, but they say for an average person, the horizon is approximately 3 miles away. I never realized that. That's kind of cool. And the higher you go, the more you can see. They gave us this wonderful fact. Everyone can do this, of course. At the top of Mount Everest, you could see approximately 209 miles away. Now, you're not picking out people or birds at 209 miles away, but that you can see that border between the sun and the sky. Sorry, not the sun and the sky and the earth. And the higher you go, the farther away it is. So that's kind of cool. Oops, not want to do that. Sorry, trying to hit my pause button here and it's not working. Odd. Okay, well, I guess I won't be pausing. No pausing for you. All right. So, I probably don't have to point this out, but on a previous slide, we just said this, the sun and all the stars move along the celestial sphere. The sun isn't moving with regards to us. You know that, right? We're moving, but it's an apparent movement is the idea, okay? The Earth revolves around the sun, and it took me a little while staring at these diagrams to wrap my brain around it. And of course, I don't think that geocentric is real, the way things work. I understand heliocentric, but all these diagrams, they make it, and even my wife is trying to, you know, not explain it to me, but calm my nerves. I'm like, this is stupid. Why are they doing it this way? She says, well, it's from your perspective. It's from Earth's perspective. That's the only one you'd know. I'm like, yeah. I still think it's confusing to show, the Earth and then the stuff moving around the Earth, even though we just said. So maybe you're not as thick-headed as I am. I don't know. But we all know, okay, that this stuff isn't revolving around the Earth. It's an apparent path as we move around it. They just felt that it was easier to explain it this way. Okay? Okay. All right. So, again, just more about this ecliptic and how we all float around in there. So this orbital plane is the ecliptic. So we rotate around the sun. If you could sort of get above the sun and look down on it, the Earth rotates around it counterclockwise. As such, okay, the sun appears to rise in the east and set in the west. Okay, and again, you know this. Sun rises in the east, sets in the west. That's due to the way we rotate. Now, it would be best for you if you use two hands. I'm simple and I'm Italian. I talk with my hands, right? But even just set, a coffee mug on the table or something in front of you right now, and take one of your hands. I'm using my right hand because I am, and put your fingers down on the table, and so that you're kind of like making a little walking thing with your fingers, crawling across like thing from the Addams Family. Okay. Rotate that hand counterclockwise. Now make your thumb or whatever is closest to the coffee cup, or whatever you're using, pretend that is the east coast of North America. And as you rotate your hand counterclockwise, you can see how first the east coast, then the states as we generally go more and more westward, how the sun moves across the U.S. in that manner. Okay, works for me. If you mess with it for a couple minutes, you'll see what I'm saying. But so because the Earth rotates counterclockwise, all right, the sun moves from east to west. Okay, Terminator. If you have an iPhone, I know this is one of the, I think it's a wallpaper, and it's pretty cool. I never really pondered it so much. My wife uses it. I don't. But it gives you that day-night line on the entire world, okay? And if you have it, poke around, look for it. I'm not sure what they call it. They might call it sunrise, sunset wallpaper. It's one of those active moving ones. And you may have even seen images out there on the interweb somewhere about this. But it is a it is a line, okay? It's not black and white. It fades in on one end, it fades out on the other end, but you could actually see from space the light and dark side slowly moving its way across the planet. And the cool thing of it is on one side is sunrise, and on the other side of the line is sunset. I really encourage you to look for that. I don't know if Androids have a version of it or not, but it is a very cool wallpaper. Two more vocabulary words, and they have to do with day. Okay, and you thought day was pretty simple. I know what a day is, 24 hours. Well, that is a solar day. Okay. And what it is that solar day, as it turns out, is with reference to the sun. Okay. But there's another day that is actually, they say, the real rotational time of the Earth. It's 4 minutes off. All right, 4 minutes off. With reference to the rest of the stars, the Earth rotates 23 hours and 56 minutes. In other words, pick one star, okay, in the sky, wait till we revolve, not revolve, rotate all the way around once till that same star is in the same place again, and it is 23 hours and 56 minutes. They call it a sidereal day. Sidereal day. Sidereal. Weird word, I know. So they say in the book here the difference is due to our irregular rotation. Sometimes we're a little closer to the sun than not. Remember the elliptical orbit stuff. And I think it also has to do with our closeness. Even at 93 million miles, we're significantly closer to the sun than any of these other stars. Next closest star, I think, is out there about 4 light years, okay, which is 26 trillion miles as opposed to 93 million miles. So we see a big, I think we see some variation due to that too. But again, 4 minutes, who's counting, right? But in reality, okay, over time, that certainly does add up. Okay, well, I was looking for my counter here, and I'm trying to keep you guys on these shorter videos, but Screencast-O-Matic is hassling me. Okay, this is really cool. If you've spent any time in a science museum, little kid or recent, you've likely seen this Foucault's pendulum, sorry. And it's hanging from usually a very high ceiling. And it's this giant pendulum that just swings back and forth, back and forth. And unless you stop to read the sign, you might have just thought it was cool for its own purposes. Okay, just fun to watch. But what's happening, you can't really see them in this one here. There's these little pegs. Now maybe these are the pegs here, but in the original one there were pegs all the way around it. Okay, as the Earth rotates, the pendulum keeps moving in the same plane. All right, because, well, physics. The Earth keeps moving in the same plane, but the dial underneath it moves. And the way Foucault proved this was by putting little bottles or cans or little pegs up, and slowly but surely each one would get knocked down in order. So it was proof, evidence that the Earth rotated. All right, you had to do something very cool up at the top to make sure that the building didn't rotate as well, so they had to put like a little Lazy Susan kind of thing up there. But very neat. So the pendulum goes back and forth in the same plane, in other words, in the same space constantly, but underneath it, this dial moves. It's like kind of like a weird watch where the hands stay in place, but the dial underneath it moves. Anywho, Foucault's pendulum. All right, how long does it take to get around the sun? So orbiting is different than rotating. Rotating is us spinning on our axis. Orbiting is what we do to go around the sun. As you know, it takes a year. Actually, it takes a year and a quarter. all right, solar days. And in order to do that, we need to travel around the sun at 66,000 miles per hour. So at 66,000 miles per hour, it takes 365.256 days to go 584 million miles. Now, I know some of you are thinking, wait a minute, you just told me we were 93 million miles away from the sun. That's right. We're not driving towards the sun. We're making a loop around it. All right, so that's circumference versus radius, if you would. All right, so this is a loop around the sun. And as you'll find out soon, it's not an actual circle. It's something called an ellipse. All right, which sounds a lot like eclipse and ecliptical. A lot of E words. Anyhow, since 1582, we've used something called the Gregorian calendar. And we knew this about the quarter day a while ago, at least by 1582, seemingly. And this is when we came up with leap year. Okay, so every 4 years we add an extra day, and it accounts for that quarter day in the orbital year. See how that works out? And if you look in the book, there's actually this, I didn't put it in here. Every century except centuries that are divisible by, I don't know, I'm making up a number now, 40 or something really bizarre like that, 400, then they don't do this. So if it's on every 4th year and it ends up being a turn of a century, and that turn of a century is or isn't divisible by some number, they don't. I figured we didn't need to worry about that, but I did read it, just so you know I wasn't skipping over it. But heaven's sake, you don't need to worry about that. Okay? All right. So leap year is tied into our orbit, and it's a way for accommodating for those that extra quarter day there. So, as I said a moment or so ago, it's not a complete circle. The planets. All right, we learned that with in our first lesson there. We learned about the history of astronomy. Their calculations worked out a lot better if we used ellipses instead of circles. Well, it turns out our circle is dang near an ellipse. All right, very, very close to an ellipse. You see a circle in red dash here, and you see the blue line that is our orbit, and they almost line up on one another. Almost line up on one another. We average about 93 million miles away from the sun. We've got 2 more vocabulary words for you here, perihelion and aphelion, okay? And peri means near, all right? And then A is not usually, so we're not close for aphelion. So perihelion is when we're closest to the sun, and I believe that is on the left side here of this diagram. And then aphelion is when we are farthest from the sun. So what I thought was kind of neat, and I'm not going to hold you to these numbers here, but that while it looks how similar these orbits almost line up, it really accounts for about 3 million miles. So that little bit there, that little bit there, that's 3 million miles. So anywho, so aphelion, perihelion, average orbit around the sun of 93 million miles, and an elliptical orbit. All right, while we're at it, I tried with this to make this is my green line here. I tried to add a bit of depth to this. I'm not good at editing images, but I tried to add another line to show that we are off of this. Again, here's your equator, okay, to show you that sometimes we're up above the equatorial plane of the sun, sometimes we're below the equatorial plane of the sun. And if you're wondering why this is even relevant, think back to our conversation about the seasons. All right. And when we want to shine the northern hemisphere versus the southern hemisphere at the sun, well, hey, then that works out. So, all right. Speaking of seasons, we're going to do one more slide here, and then I'm going to pause this recording so I can try to figure out why the screencast-o-matic isn't really working for me here. So there were, in your book, there were 3 pictures that went along with this one. I kept just the one in the center here because this is roundabouts where we are. Utica is actually 43 north. Or Orlando, Florida is 28 north. I Googled those. So 35 north, you're roundabouts. I could have just Googled where that is. I'm going to guess that you're roundabouts Maryland, let's say. Okay. Anywho, so if you were standing in Maryland and at the surface of the Earth, this is where you would expect to see the sun peaking each time at noon, okay, during the day. And I find it odd because it's never, in the summer it's dang near right overhead, but it's always off to the south, all right? And you may have known that. You may have known that already. Some people know, where to plant gardens and the best place for gardens, and nowadays solar panels on roofs, and they need to know, well, do you have a southward facing or is it a northward facing? It comes up in a lot of applications, but for the rest of you out there, and myself, because I don't always remember these things, this is where, again, rise in the east, set in the west, as it changes over the year. And what that's supposed to line up with, of course, is our seasonal diagram here, which is all in one plane. And that's what I was fretting the most about. I told you I was grumbling to my wife about these diagrams and why can't they keep them straight. We spent the time when we learned the seasons with this diagram, and it has everything going around in one plane. They perhaps could have introduced at this point the idea that, hey, we go up, we go down, we go up, we go down. It's not flat and level. But, hey, I didn't write the book, right? All right, folks, I'm going to end this first section of the lecture here. Talk to you again in a minute.